Hi everyone. In the last lesson, we talked about how we can use the inductive effect to answer questions. In this lesson, we are going to talk about delocalization and resonance. Alright, so you would have come across the terms delocalization and resonance in your notes somewhere or another. Alright, so let me explain it to you. Alright, so previously we said that for inductive effect, it goes through the sigma bond. All right, this for inductive. So this time around, whenever we talk about resonance and delocalization, we are interested in the p orbitals and the lone pairs of electrons uh, overlapping. All right, so you must have a p orbitals and lone pair of electrons overlapping in order for you to exhibit resonance and delocalization. So let's take a look at the few examples here. Right, I think you should be able to notice that at each of these carbon here, alright, they are all sp2 hybridized. Even this carbocation is sp2 hybridized. Alright, so therefore, since they're all aligned, there is a form of delocalization. Right, so this is how the pi electron clouds can interact. On the other hand, if we consider this example of a phenol, right, we have all our pi electrons, okay, our p orbitals in the benzene ring, right, and we also have a lone pair of electron on oxygen, and this allows all of them to allows the lone pair of electrons to delocalize. Is the same thing happens for this chlorine atom. All right, because of its lone pair of electrons in its p orbital is able to delocalize once again. And then lastly, right, take note that we have a pi bond here, so p orbital, and then we have lone pairs of electrons here. All right, so these three things allow us to delocalize. Okay, so this is the idea behind delocalization, where p orbitals and lone pairs of electrons actually overlap. Okay, so let's go deeper and look at these examples. All right, because sometimes we will know that electrons somehow seems to flow into the ring, delocalize in the ring, and sometimes it seems like electrons delocalize out of the ring. So let's try to understand this phenomenon, right? But just a word of caution, right? Whatever I'm going to explain now is just the thought process. It's just for illustrative purposes. It is not exactly accurate, right? But I still see value in showing you that. Okay, so let's take a look at this. Right, so let me erase everything off. Okay, previously we have already established the fact that there will be delocalization and all of these things. So let's just do a very simple let's just do some very simple mathematics here. All right, so we know that we have a lot of p orbitals here, and in each p orbital we have a certain number of electrons. So let's try to label them. So I have one here, one, and in this p orbital here, all right, there is 0, right? So I have 7 atoms, 6 electron. All right, in the second case, I have 1, and 1 in the p orbitals. Here I have a lone pair, so I have 7 atoms, all right, and 8 electrons. All right, likewise, for this example, we also have 7 atoms and 8 electrons. So which are the 7? These are the 7 that allows us to delocalize. All right, so I have 1, and 2 here. So take note, I am only interested in the p orbitals that overlap, so I'm not interested in these other bonds here, and I'm not interested in this hydrogen atom. All right, just the p orbitals and the lone pair of electrons. Okay, and then in our last example, all right, we have one here, and 2 here. Okay, so this is a lone pair of electrons, this is the p orbital, this is the p orbital. One electron gives us the pi bond. Okay, so this for the last example, I'm not going to talk too much about the number of atoms and the charges, but I hope that in these two examples, all right, in the first two examples, you're able to see that if I have 7 atoms and 6 electrons, right, the final electron density of all my atoms will be 6/7. So I take the number of electrons divided by the total number of atoms. Alright, and as you can see, this carbocation here started off with 0. Now it has 6/7 electrons. So this shows that now the electrons have flowed, have just like flow into this carbocation. Alright, and then in the ring, it went from 1 to 6/7 electrons. That's the reason why we say that well, the electron density actually flow towards this carbocation. Whereas in the other case, now we have 8/7 electrons. Alright, so the oxygen atom went from 2 to 8/7, which is decrease, while the ring went from 1 to 8/7 electrons, which is an increase. Okay, so this illustration should show you why the electrons in this in the example of a carbocation, alright, the electrons flow out of the ring into this carbocation, whereas in the other example, it flows from the oxygen atom into the ring. Right, so this is to explain the difference. However, the reason why I said this is just an illustration and not completely true is because we haven't really taken into account of the electronegativity difference. Alright, and this is going to affect where the electron actually lies. So let's take a look at phenol versus our carboxylate. So in the next few lessons, you'll learn about the stability of conjugate bases which will determine the acidity of a weak acid. Alright, so we want to compare the common two examples that we compare is phenoxide and this carboxylate. So what we say is that the lone pairs of electrons, or rather the negative charge, is delocalized into the ring. Alright, so it is dispersed. Likewise, we say that this lone pair, this negative charge is dispersed between these two atoms. Right, that is why it is the conjugate base is more stable. But we know that a carboxylate ion is more stable as a conjugate base than phenol. Alright, and this reason is because of the more electronegative oxygen atom. So because both of these are delta minus, so this tug of war shows that both of them actually share it to almost the same extent. So the electron density is more or less concentrated towards the center. Okay, whereas in the other case, right, most of the electron density on this oxygen atom, right, still stays near oxygen, even though it's delocalized into the ring, because oxygen is more electronegative compared to the rest of the carbon atoms. Alright, so you have to take into account both the electronegativity difference and also the number of electrons within this whole system. Alright, so this the idea of resonance is not that simple. Right, so if you are confused, do watch this video again to make sense of it. Thank you.